So this lesson is on conduction and convection. Okay, so the lesson objectives for today. By the end of this lesson, you should be able to state the various ways in which thermal energy can be transferred through different mediums, through solids, liquids and gases. You should be able to explain using the kinetic theory model, which we've already covered, how conduction and convection occur. And you should be able to explain why conduction and convection do not occur in all mediums. So why doesn't conduction occur in liquids and gases, or why doesn't it occur well in liquids and gases, and why doesn't convection occur in solids? Right, I thought we'd start by recapping the difference between thermal energy and temperature. It's a really important difference that we really need to get our head around. So the temperature of an object tells us how hot or cold it is. It's a measure of the average kinetic energy of an object's particles, and we measure it in degrees Celsius. So the thermal energy, however, is the total amount of kinetic energy and is measured in joules because it's a type of energy. The example that I always use here is a small cup of boiling water and a huge iceberg. Now, within that small cup of boiling water, the particles are absolutely going crazy. They're vibrating all over the place. They have a huge amount of kinetic energy. They're moving very, very fast. But because it's a very small cup of water, if we were to add up the total amount of energy of all of those particles, it would still be much, much lower than in the iceberg. Obviously, in the iceberg, each particle is moving very slowly, only vibrating a very small amount, but because there's so many particles, if we add them all up, or the energies of all of those particles up, the total amount of energy is going to be very, very high. Okay, so just keep that in mind when we're going through the rest of the unit on thermal energy. Okay, so we're talking about heat transfers. We're talking about thermal energy moving from one place to another. Now, that happens in 4 ways. Before we get onto those 4 ways, I want to talk about the fact that it always moves from regions that are hotter to regions that are cooler. It's incredibly important that we always talk about the movement of heat, never the movement of cold. So it's very easy to fall into that trap because sometimes it might seem like the cool or the cold is moving. So for example, if you put a hot object into a cold room, that hot object is going to cool down, and it might get the impression that the cold is moving from the surroundings, from the outside, into that object. That is definitely not what is happening. What is happening is the thermal energy is moving from the hot object into the surroundings, therefore heating those surroundings up. But as a result of that energy moving out of the hot object into the surroundings, the hot object's thermal energy is decreased, so the temperature is going to have gone down. So you get the impression that that cold has come in, but it isn't. What's actually happened is the heat has moved out. It is very, very important that you always talk about the heat moving, never, never, never the cold. So anyway, this happens in 4 different ways. So the first is via conduction. Now, conduction does take place in solids, liquids and gases, but it is very inefficient in liquids and gases for reasons we'll talk about in a while. So generally, conduction occurs in solids. We've then got for convection taking place in liquids and gases. Again, for reasons we'll discuss in a while, it definitely does not happen in solids. And then via radiation through gases and through vacuums. Now, in year 8, we'd have stopped there, but for the GCSE, we also need to look at a 4th different method of heat transfer, and that is via evaporation. So that's when thermal energy is able to move from a liquid to a gas, and we'll talk about that in another lesson. In this lesson, it's just about the first 2, conduction and convection. So we're going to start with conduction, which is the flow of thermal energy through a solid. As I've said before, it does occur in liquids and in gases, but nowhere near as effectively for reasons we'll discuss in a second. So we're talking about this happening in solids. Now we're going to start by talking about what happens when an object heats up. Now what happens is the particles gain kinetic energy. They start vibrating more vigorously around their fixed position in that solid. And I think this is a really key part of any explanation of conduction. So you always start by saying that the particles closest to the heat source gain kinetic energy. Now here we can see the lattice in which these particles inside the solid are arranged. What we do want to point out with this diagram, in reality, these particles are pretty much touching each other. We always talk about the fact that solids are incompressible because they can't be pushed any closer together. So this diagram isn't quite right in the sense that it doesn't show them quite close enough. But what we've got here is our heat source here down at the bottom, increasing the kinetic energy of this particle here. That is then going to collide with this particle and with this particle, and it's going to cause them to start vibrating also. So that kinetic energy is being passed on to those two particles, neighboring particles. Those are then going to collide with their neighboring particles and cause them to vibrate also, and in that way that kinetic energy is going to get passed along the line from one particle to the next. So here is an explanation of what we've just seen. So the particles in the solid are arranged in a rigid lattice. That's the diagram we've just seen. And so when the kinetic energy of one is increased, that's the one closest to the heat source, it's going to collide with its neighbours, causing them to vibrate also. You need to remember these things are really tightly bonded together. There's very strong bonds between them. So if one starts vibrating, the one next to it has no choice but to also start vibrating. And in this way, that thermal energy is passed from one particle to the next. I've bolded and underlined the word collides here because it is one of the words that tends to come up in the mark schemes when you're talking about conduction. So try and make sure that you use that word when you're describing conduction. Okay, so different materials conduct thermal energy at different rates. We know this. You would never use a metal spoon to heat up some food because you'd very quickly burn yourself. You're going to use a wooden spoon instead, because the wooden spoon is not going to conduct the heat away from the saucepan or away from the food up to your hand and cause your hand to burn, whereas the metal would do that. So materials that let the heat pass through them very easily are what we call good conductors, and like I said, an example of this is a metal.
Let's zoom in and look at the particles in the glass and see how it conducts. So glass is a typical solid in the way it conducts. The particles by the fire start to gain heat from it and start to vibrate much more vigorously. They then collide with the particles next to them, passing on the energy, and slowly down the rows each particles vibrate more and more vigorously, passing on heat to the next one through collisions. So it progresses slowly through the glass. This is how conduction happens in most normal solids. Right, now let's look at the metal and see why metals are such amazing conductors. If we look at the metal, we see there's still the same process happening as in the glass. The atoms near the fire are gaining heat and vibrating and colliding with the ones next to it. But there's an extra thing happening inside of metals. There's all these tiny little electrons whizzing around. They're called free delocalized electrons. They can bump into all the ions throughout the metal, so they can gain heat from the hot end and race straight down and bump into an atom at the cold end, therefore spreading the heat through the metal much, much quicker. This is why metals are so amazing at conducting.
So here I have a conduction demonstration. I have a bar that has a piece of paper wrapped around it. I'm going to heat that piece of paper over a Bunsen burner. I'm going to keep it moving. I don't want to heat it up too quickly, but we should see very quickly that some of the paper burns and some doesn't. And we can see here we're getting a very, very distinct line. This side of the paper hasn't burnt, this side of the paper has. Now that's due to the material that the bar is made out of. You'll notice that on this side we've got wood, and on this side we've got metal. Now because the metal contains free electrons, it's a very good conductor and therefore is capable of conducting the heat away from the paper, stopping it from burning. Whereas on this side, the wood is not a good conductor, it does not contain free electrons, and therefore the heat cannot get out of the paper, it has nowhere to go, and so the paper heats up and ends up burning.
Now, as we've just seen from that animation, metals are really good conductors because not only is that thermal energy being transferred from one particle to the next via the collisions, but we've also got these free electrons, what a chemist might call delocalized electrons, that are able to move freely throughout the material. Now, when they're doing that, they're going to be colliding with that lattice of vibrating ions, picking up thermal energy, moving to another part of the material, colliding with another particle, and then passing that energy onto those. Now that process is going to happen much, much quicker than just relying on the particles colliding with each other. So the presence of those free electrons that are able to move freely throughout the material is going to massively speed up the transfer of thermal energy throughout the material. Now, different metals contain different numbers of free electrons, and so the metals that contain more free electrons are going to be much better conductors than metals that contain less. All metals do conduct free electrons, so all metals are good conductors. But some, say for example silver or copper, contain a lot more than others, something like aluminium, and that would make silver and copper much better conductors than aluminium. So, like I say, different metals conduct thermal energy at different rates due to the difference in the number of free electrons present in those materials.
Okay, I have another conduction demo here. This metal star has got pins attached to the ends of each of these bars using wax. Each bar is made out of a different material. What I'm going to do is to heat the center here. We're going to see the heat being conducted along each bar. When it gets to the end, it will cause the wax to melt and the pins will fall. If we go ahead and do that now. So just a reminder, with conduction, the particles closest to the heat source are gaining kinetic energy. They are vibrating more vigorously. They are then colliding with their neighbours, causing them to vibrate also. With metals, there are free electrons within the material that are able to move freely, thus transferring that kinetic energy. We've seen that the 2 pins have already fallen, so that wax has melted. Those 2 are obviously the best conductors. We've just seen another one fall now. The 2 that are remaining are the worst conductors. The difference in conduction is due to a difference in the number of free electrons present within that material. Hopefully, if we leave it a couple more seconds, we should see that the other 2 melt and those pins fall. There we go. So this tells us A, that conduction is taking place, and B, that different metals conduct thermal heat at different rates. That last one is obviously the worst conductor, so therefore has the least number of free electrons within the material. Just a reminder that silver is going to be the best thermal conductor because it has the most free electrons per unit volume. This last one obviously not a good conductor because that pin has still not fallen. We're having to raise it to a significant temperature. The heat is obviously not finding it particularly easy to move through that bar down to that final pin. There we go. So clearly this is the worst conductor. I think this was the first one that fell, so that tells us that's the best conductor.
So other materials are not good conductors. Now we call these materials insulators. Some examples of this might be wood, water and air. Now wood is a poor conductor because it doesn't have any free electrons. It's purely relying on the collision of those particles. It does happen. Wood will conduct heat. Materials that don't contain free electrons do conduct heat. They just don't do it very well because they don't have those free electrons that are able to move throughout the structure. Things like fluids, so like water, also very poor conductors. You remember, in those solids, you've got a really tightly bound lattice, and one particle vibrating is going to cause the neighbouring particles to vibrate also because they're so tightly bound together. And don't forget from our lesson on the kinetic theory model that the difference between a solid and a liquid is the fact that we've broken some of those bonds, and so they're not as tightly bound to each other, and so one particle vibrating is not going to transfer its energy to a neighbouring particle quite as effectively. Again, it does happen, it just doesn't do it as well as it happens in solids. You obviously also don't have free electrons in water, and so or any fluid, and therefore that makes it a poor conductor as well. Finally, air. Now, gases are really bad conductors because their particles have completely broken their bonds and are really far apart. And so because of that, one vibrating over here, going crazy over here, is not going to affect another one over here. Why have I done that in red? Here we go. One over here. So these guys are, this one is vibrating, going crazy all over the place over here, and it's just not going to collide with this guy over here, and therefore we're not going to get any kind of thermal energy being transferred between the two. They are going to collide very infrequently. So again, things like gases, things like air do conduct, they just do it incredibly slowly. They are not going to be good transfers of thermal energy via conduction. Okay, so when answering any question on conduction, it's really important that you start by talking about the fact that the particles closest to the heat source have gained kinetic energy. It's also then really important that we talk about the fact that the particles are going to collide with each other and transfer energy. I'd also put in here the fact that the particles are very tightly bonded together, strong bonds between those particles, and so that transfer of kinetic energy is going to be very efficient. In the case of metals, it's then very important that we talk about the presence of free electrons or delocalized electrons that can move freely within that material, thus transferring the energy at a much higher speed. And the other thing that we need to be aware of with conduction is the fact that gases, things like air, are very poor conductors because those particles are not tightly bound to each other. They're very far apart, they collide very infrequently, and therefore are not very good at passing kinetic energy from one to the other via collisions. So conduction does not occur effectively or efficiently in liquids and gases, and we've just been talking about why. So how does heat get transferred through a liquid and a gas? Well, one of the main ways that happens is via convection. So convection takes place in liquids and gases. Now, there's a word that we use to describe both liquids and gases, and that is a fluid. So I might use the word fluid. A lot of people only apply that to liquids. Fluid can be used to describe both liquids and gases. So again, where we're going to start is what happens when the air closest to the heat source heats up. And what is happening is the particles in that region are gaining kinetic energy. Now, we've already done a lesson on thermal expansion, so you should already be able to describe what happens when those particles gain kinetic energy and start vibrating more vigorously. What happens is they move further apart, so they spread out. Now, that's going to have a serious impact and is very important for the process of convection. So these particles have spread out, the spaces in between them is increased. And because of that, they're now taking up a greater volume. Now the number of particles has not changed. You've still got exactly the same number. We haven't lost any, we haven't gained any. So the mass of this substance is still going to be the same. So you've got a greater volume, but the same mass. Now, if you think back to the work we did right at the beginning of the year, make my pen up here, we've got the equation density is equal to mass divided by volume. Now, if we've got the same volume, the same mass, but a greater volume, if we make the number on the bottom of that fraction bigger, the density is going to decrease. We're going to get a smaller density. So because the volume has increased and the mass has stayed the same, we've got a smaller density. That density has gone down. You can see that in these diagrams here. We've got the same number of particles in both. I don't know why the one on the left isn't animated, but I'm not going to spend a huge amount of time trying to get that sorted. It's not really important. The point is, same number of particles, but on the right we've got a greater volume, and so they're much further apart. The density has gone down. So because the density has gone down, that gas or liquid, that fluid, is going to rise. And when it rises, it's going to cause a low pressure in its place, and that's then going to draw in cooler, denser liquid. You can't have a vacuum there. If this hot air, this hot fluid rises up, you can't have nothing left in its space. And so what happens is, like I said, that pressure drops and it's going to draw in cooler, denser liquid or gas from either side. And in this way, we get what we call a convection current being created. Now that term, convection current, is an important one that you really need to be familiar with and try and use in any kind of answer about convection. And I'm going to show you a couple of examples of the kind of convection currents we see. So this is the first type of convection current. We have here in the bottom left-hand corner a radiator. The air that is in contact with that radiator is going to be warming up, so the particles are going to be gaining kinetic energy. They're going to be vibrating more vigorously, so they're going to move further apart. Because they've moved further apart, the density of the air in that region is going to fall. And because the density has gone down, that hot air is going to rise, and we can see that happening. It gets to the ceiling, has nowhere to go other than across the room. Again, when it gets to the top, or the far right-hand side of the room up here, it's then going to start moving downwards. It's effectively going to get pushed down by the air that's coming in from over here. And obviously, because of the fact that this air is rising here, you're going to get cooler, denser air being drawn in here. Okay, so this is a typical kind of convection current that you would get in your living room if you've got a single radiator. Let me just take out these arrows. Interestingly, if you had another one over here, so if I had another radiator on this wall here, we are going to get a convection current moving in this direction. They're going to meet here, and then they're going to both come down here, and you're going to get two convection currents being set up like that. Okay. So this is another convection current that I want you to be aware of. In the day, the land is going to be much warmer than the sea. Now, we've already talked about specific heat capacity. So water has an incredibly high specific heat capacity. So it takes a lot of energy in order for it to heat up or cool down. It also has a very large mass. If you think about the mass of the sea, it's huge, and it's also moving around all the time. So to heat it up effectively is going to take a huge amount of energy. It's therefore going to take a lot of time. So the sea does not warm up as much as the land during the day, and therefore the air above the land is going to get warmer. It's therefore going to become less dense due to those particles vibrating more vigorously, moving further apart, and therefore it's going to rise. Again, you're going to end up with this low pressure over the land, which is then going to draw in more cooler, denser air from the sea. It's why we tend to always get onshore breezes when you're by the coast. This isn't always necessarily the case with Jersey, because obviously France is what really dominates our weather systems. But certainly if you were to go to France, you're going to get this onshore breeze throughout the day. Interestingly, this actually reverses at night, where you tend to get the land cooling down very rapidly, and sometimes in the evening the wind switches and you end up getting an offshore wind throughout the night.
Okay, what I have here is a convection demonstration. I would usually place a candle in here, but for the video I've decided to use some fire lighters, so I'm just going to get more heating effect. But what's happening is the air above the candle is being heated. The particles are gaining kinetic energy, so are vibrating more vigorously, and are therefore moving further apart. This is causing a decrease in the density, which causes the air to rise out of this tube. A low pressure is then created in the chamber, which draws air in down this tube and along. And we can't see that at the moment. If I light this piece of paper in order to generate some smoke, and I place this over here, we can see that smoke being rapidly drawn down that tube, along through, and then out of here. So a really nice demonstration of convection, which again is caused by a decrease in the density of the air above the heat source, which is a result of the particles moving further apart because they have gained kinetic energy and are vibrating more vigorously. Okay. So this is a really nice demonstration of convection. We have here a convection tube which is filled with water. I'm going to ask Dr. Cook to cut away to a photo of the level of the water so you can clearly see that. It's going to be important in a second. And what I'm going to do is I'm going to place some potassium permanganate into the tube. I don't need a lot, it's just to dye the water so we can see what's happening. Now, if I now place a heat source below one side of the tube, the water in this region is going to start heating up. So particles are going to gain kinetic energy. They're going to therefore vibrate more vigorously and so move further apart. As a result, the density in that region is going to decrease, which is going to cause the water to rise up this tube. That is going to cause the cooler, denser water to be drawn in down this tube and along, and we can see the potassium permanganate being drawn in and along. This causes what we call a convection current to be set up. That's a circular motion of the fluid rising above the heat source and being the cooler, denser liquid being drawn in. Interestingly, if I move the heat source over to the other side, if I place it here, we should see quite quickly the reverse happening. So in this time, we're going to see the heat source on this side causing the water on this side to heat up. Particles therefore vibrate more vigorously, they're gaining kinetic energy. They therefore spread out so the density decreases, and we can see then the convection current is operating in the opposite direction. Okay. Now, I'll put that to one side. I'm now going to take another photo to show you the level of the water now. So as you've just seen from the photograph, the volume of the water is increased. That's due to the thermal expansion of the liquid, which really is what's caused this convection current to be created in the first place. So just to summarize, when we placed the heat source on this side, the water in that region became less dense due to the expansion, causing it to rise, cool the denser liquid drawn into a place of it, and in that way a convection current was created.
Okay, so I'm going to summarize convection now. Now actually with this, I think it's really important that you write this down in these numbered steps, because it's very easy to skip one of these steps. You know, you can jump straight into, for example, the fact that the density's gone down, or just skip out talking about density altogether, and you're going to lose loads of marks. So in your notes, definitely make sure you have this numbered list of steps to go through to help you remember the order in which they occur. So like with conduction, we're going to start by saying that the particles closest to the heat source gain kinetic energy. It's a really important step. It's fundamental to what's happening. We're then going to talk about the fact that those particles move further apart. So exactly the same explanation as you would use if you were talking about thermal expansion. Now, because those particles have moved further apart, we're going to get a decrease in the density of the fluid in that region, and then that fluid is going to rise as a result of the decrease in density. We then talk about the cooler, denser fluid being drawn in to replace it, which in turn is going to get heated up and is going to rise. More cooler, denser air is going to be drawn in. And then we're going to finish by saying a convection current is created. So 6 very clear steps that you must go through. Do not jump straight from particles gaining kinetic energy to the fluid rises, or don't go straight in with hot air rises. You need to go through these steps. If you don't, you are going to lose marks in an exam. Okay, and just to finish off our work on convection, I just want to talk about why convection doesn't happen in solids. I think it's quite an obvious one, but convection does not happen in solids because the particles in the solid are in a fixed position. They cannot move freely around. So when you get that change in density, when those particles start to vibrate more vigorously and move further apart, it does cause a decrease in the density, but because of the fact that the particles cannot move around freely, that you don't get that rising effect that you get in liquids and gases. Okay, right, I'm just going to finish off by asking a quick question, get you something to think about before our next lesson. And that is, how does the energy from the sun get to Earth? Now, I'm hoping you can rule out conduction and convection, and I want you to think about why we can rule out conduction and convection in terms of the energy getting from the sun to the Earth. And in our next lesson, we'll talk about the answer to that question.